January 5, 1943, the Pacific Theater. A Japanese Aichi dive bomber screams toward the cruiser Helena. Anti-aircraft batteries open fire. No direct hits, but the plane disintegrates in mid-air. Suddenly, Allied guns became lethal. Overnight, the effectiveness against enemy aircraft surged. Then, the barrels turned toward the German infantry. The results were horrifying. The Allies possessed a secret, a breakthrough that would redefine the cost of war. But to understand the leap, we must look at the butcher's bill of the past. In the First World War, the machine gun didn't claim the most lives. Gas didn't either. 75% of all casualties came from one source: artillery. By the 1930s, generals still called it the king of battle. They operated on three rigid principles. First, counter-battery fire, a blind duel. You find their batteries before they find yours. Second, interdiction, reaching deep behind the lines, shredding supply trucks and reserves before they ever see the front. Third, direct support, hammering the earth in front of your own infantry with high explosives. Before the breakthrough, this was a game of statistics, not precision. Batteries fired thousands of shells to hit a single coordinate. Early artillery accuracy was less than 10%. While generals spoke of the king of battle, the reality on the front line depended on a scrap of paper. The battery receives approximate coordinates. Now, the geometry of death begins. A navigator's hand grips a pencil. It traces a jagged line across a paper map. The ruler trembles. Sweat hits the sheet, blurring the grid. He calculates wind, elevation, and charge by hand. How do you hit a target you cannot see? You rely on a stranger with a bad connection. Static screams through a wired telephone. A forward observer crouches in the mud, peering through binoculars. He shouts corrections over the roar of incoming steel. The battery waits. Before the war, planners envisioned a lightning-fast, motorized juggernaut. The reality was a regression to 1916. Horses still pulled the bulk of the guns. Wood and leather met grease and iron. Armies relied on the same blunt doctrine: soften the enemy with days of mass bombardment. Victory was a matter of industrial weight, not surgical precision. The flight of a shell took seconds. The calculation of its path took minutes. The battery fires a salvo. The crew freezes. They listen to the crackle of the radio, waiting for the observer to confirm the impact. Tactical errors on the map were corrected with raw mass. If the math failed, the caliber grew. Generals replaced precision with industrial gigantism. The arsenal followed two paths. Field guns fired flat, tearing through everything in their direct line of sight. Howitzers took the indirect route. They sent heavy steel screaming along a curved trajectory to crush targets hiding behind hills. For the infantry, the solution was the mortar: high angles, close support, light enough to carry, fast enough to deploy. Can a human fit inside a cannon? An 80-centimeter bore says yes. The scale of the tools defined the carnage. On one end stood the 20-millimeter autocannon, rapid, precise. On the other, the heavy 155-millimeter howitzers. But then came the exceptions. The Schwerer Gustav moved on railway tracks. Its caliber was 800 millimeters, 31 inches of solid steel. 20 millimeters versus 800. The gap was a factor of 40. German engineers watched the giant crawl toward the front. The 800-millimeter monster meant nothing without the small piece of steel on its nose. If the fuse failed, the giant was just a high-speed delivery of scrap metal. A soldier's hands are black with grease and frozen mud. He picks up a detonator. The threads are clean, oily, and catch the light against the dull casing of a high-explosive shell. He screws it in. Slowly. This is the moment a heavy cylinder becomes a weapon. What happens if a loader drops the shell? Nothing. Internal safety mechanisms prevent arming until the moment of firing. The crew survives their own clumsiness. Artillery remained a game of evolution, not revolution. Calibers grew to feed the hunger for power, but the mechanics stayed the same. It was the payload that changed. High explosives leveled fortifications. Shrapnel cleared trenches. Anti-tank rounds pierced steel, while smoke and illumination blinded or exposed the enemy. In China, the Imperial Japanese Army added a darker layer to the arsenal. They deployed poisonous gas. To hide the crime, they disguised the chemical rounds as ordinary smoke shells. But the standard was the point-detonating fuse. It was simple, it was reliable. The firing pin struck the primer only upon physical contact with the target. Direct impact was simple. You aim, you fire, the shell hits a target and detonates. But the battlefield demanded more than just a collision. Why does the Earth save infantry from an explosion? The soft ground acts as a sponge. It absorbs the blast and traps the jagged steel shards before they can reach the target. To kill men in a trench, you need an airburst. You need the shrapnel to rain down from above. Engineers responded with the mechanical time fuse. It was a clockwork heart inside a steel body. The battery commander could set a timer for any window between 0 and 30 seconds. It seemed like the perfect solution to the bunker and the trench. But mechanics hit a wall. In the heat of combat, 3 seconds of flight is a lifetime. 30 seconds is an eternity. A plane or a sprinting soldier moves 100 meters every second. To catch them in the air, your math must be flawless. The battery needed to calculate the exact moment of intercept. If the timer triggered a fraction of a second too early, the blast spent itself in the empty sky. A fraction too late, and the shell buried itself in the mud before waking up. Mechanical gears were too slow to trick time. Metal and springs reached their physical limit. To hit a moving target in the clouds, the fuse needed to think for itself. Officers stood by their guns and looked at the sky. Can a mechanical computer predict where a bomber will be in 20 seconds? In theory, the math was perfect. In the field, it was a gamble with steel. The defense was a silent, cold-blooded machine. Deep in the concrete bunkers, the air hummed. Low-voltage electricity pulsed through miles of buried cables. This was the brain of the FLAK batteries, the Kommandogerät. A massive mechanical computer, a labyrinth of gears and brass, sat at the center of the command post. It breathed data. Radars and searchlights scanned the dark, feeding the machine altitude, speed, and course. The computer crunched the numbers in real time. It didn't just aim, it predicted the future. This data flowed out to batteries of 4 to 8 guns, all linked to the central nerve center. The gun crews were no longer marksmen. They were operators. They dialed the machine's logic into their sights. The system could even trigger the firing mechanism remotely. One command. All barrels recoiled at once. At high altitudes, physics took over. A shell needed up to 20 seconds to reach the target. The gunners weren't firing at where the planes were. They were firing at where they hoped the planes would be. But the future is volatile. Despite the revolutionary German tech, the math often failed against the wind and the clouds. The Allied strategic bombing campaign forced the Reich to burn through its reserves just to stay alive. Precision was a myth. To down a single aircraft, the batteries fired 3,000 shells. 3,000 shells for a single kill. This was the brutal math of the German anti-aircraft batteries. The legendary 88mm guns, the Oct-Oct, formed the backbone of this wall. Is mechanical precision enough to hit a speck in the sky? The answer was no. The guns relied on a central fire control system. It fed perfect coordinates to the batteries. Soldiers didn't guess. They used an integrated fuse setter on the gun itself. They dropped the shell into the device, it dialed the time, and the loader rammed it home. The goal was never a direct hit. Radar and rangefinders were too crude for that. Instead, the Germans aimed for the space around the target. These shells were designed to shred. At the set altitude, the casing shattered into thousands of jagged steel teeth. They tore through everything in a wide radius. Allied bombers were fragile giants. They were built from nothing more than thin aluminum skin and plexiglass. One fragment could sever a fuel line or kill a pilot. From the ground, the crews watched their work. They saw the sky fill with those iconic, deadly black puffs. But the cost was staggering. 3,000 rounds of ammunition weigh as much as 2 fully loaded railway cars. All that metal, all that powder, just to bring down one plane. The sky turned black with smoke. While the Luftwaffe bled over Europe, the Pacific became a graveyard of steel. The threat was no longer just tactical, It was existential. A single well-placed torpedo or a dive bomber could erase a carrier from the map. Then came the kamikazes. They didn't just drop bombs, they were the bombs. How do you stop a pilot who has already decided to die? You bury him in lead. The American response was brutal and systematic. Forget precision, focus on density. The fleet became a single massive organism designed to breathe fire. Every available inch of deck space vanished under gun mounts. At the heart of this steel forest stood the Iowa-class battleships. They were giants. When all barrels opened fire, the vibration didn't just shake the deck, it rattled the bones of every sailor on board. The numbers were absurd. An Iowa-class monster carried 20 quadruple-mounted 40mm Bofors guns. Dozens of 20mm Ehrlichens lined the rails. 50 caliber machine guns filled the gaps. It was a wall of flying metal. One ship could spit out several tons of ordnance every 60 seconds. Contrast the scale. You have a fragile plane made of wood and canvas facing 10,000 pounds of screaming hot steel per minute. Multiply this by an entire task force. Hundreds of barrels slaved to a single purpose, saturating the air until it was more lead than oxygen. The sky vanished behind a curtain of tracers and high explosives. Yet through this storm of splinters, the Japanese aircraft continued their dive. How do you hit a target that wants to die? A wall of fire was not enough. The Japanese pilots learned to break the math of the Allied guns. They refused to fly straight. A pilot pushes the stick forward. The engine screams, drowning out the muffled thuds of anti-aircraft fire. He is not just flying, he is hunting. The pilot drops the nose into a high-speed dive. He pulls up at the last second, skimming the waves. He zigzags. He shifts altitude every few seconds. The ship's radar works perfectly. The fire control system calculates the lead. But the calculation is a snapshot of the past. By the time the 5-inch shell reaches the coordinates, the pilot is gone. He is 50 feet higher or 20 feet lower. The system fails because of a human choice. 5-inch naval guns function like heavy German FLAK. They relied on time fuses. A sailor set the mechanical timer based on the radar's best guess. The shell left the barrel. It traveled miles. It exploded exactly when it was told to, but exactly was the problem. If the fuse was set for 4 seconds and the plane dived at 3, the shell was useless steel. It exploded in empty air. High explosive bursts bloomed too far above or too far below the target. The ships fired thousands of rounds to compensate for the error. They tried to fill the sky with metal, hoping for a lucky strike. They needed a direct hit or a perfect timed burst to stop a 55-pound shell from flying harmlessly into the ocean. The wall of steel was a desperate gamble. To stop a single bomber, 5-inch guns had to vomit thousands of shells into the clouds. It was a lottery played with 55-pound rounds. The odds favored the pilot, not the gunner. Then the math changed. In 1940, British engineers drafted a radical blueprint. They didn't want a better timer. They wanted a tiny, thinking sensor inside the nose of a shell. A device that would sense the target and detonate on its own. No more preset fuses. No more manual calculations. How high was the stakes? The British passed these radio circuit concepts to the United States. They needed American factories and American labs to turn a sketch into a weapon. Washington understood the gravity immediately. They classified the project as top secret gold. The security clearance surpassed the requirements for the atomic bomb. American engineers at the Section T laboratory began the impossible task of miniaturization. The security clearance was absolute. In the midsummer of 1942, American engineers moved the project from theory to the assembly line. They faced a physical impossibility. A standard 5-inch naval gun generates 20,000 Gs of acceleration at the moment of firing. Imagine the impact. 20,000 Gs is equivalent to a car hitting a concrete wall at 500 kilometers per hour. What happens to a glass vacuum tube during an acceleration of 20,000 Gs? Without protection, it turns into dust. The glass shatters. The delicate filaments snap. The heart of the weapon dies before it leaves the barrel. The engineers found a solution in the chemistry of stability. They didn't just mount the electronics, they buried them. The entire radio assembly, transmitter, receiver, and trigger was encased in a solid block of dental wax or specialized resin. Liquid poured into the fuse housing. It hardened into a shock-proof tomb. The glass survived because it had nowhere to move. The potting compound absorbed the violent energy of the rifled barrel. The first field tests revealed a strange flaw. The sensors were too sensitive. They didn't just react to metal wings, they triggered near waves. They triggered near the firing ship. In 1942, the ocean surface became a graveyard for local wildlife. Early fuses mistook seagulls for enemy bombers. Thousands of unfortunate birds were vaporized mid-air by high-explosive shells. It was a lethal, unintentional calibration process. Refinement took months of trial and error. By the peak of the war, the technology stabilized. The result was a mathematical slaughter. Comparative testing showed that proximity fuses increased the kill rate by more than 50%. The solution was found not in massive generators, but in pharmaceutical fragility. Engineers faced a wall: how to keep a battery alive for years in a damp warehouse. Standard batteries leaked. Corrosion destroyed them before they ever saw a ship. How do you preserve a charge for a shell that might sit for 3 years? The answer was a tiny glass ampule. Inside this vial sat a concentrated electrolyte. It stayed sealed, physically separated from the electrodes. The battery was dead. It was a cold, inert piece of metal waiting for a trigger. The glass was the heart of the weapon. Imagine a 5-inch naval gun. The shell sits in the breech. At the moment of firing, the world explodes. 20,000 Gs of force hit the projectile. Metal screams. In the center of the shell, the glass ampule shatters. You would hear a sharp, crystalline snap if the roar of the cordite didn't drown it out. The liquid spills. It floods the electrodes. In a fraction of a second, the chemical reaction begins. The miniature radar wakes up while the shell is still screaming through the air. The internal battery only activates after the shell leaves the barrel. Scaling production for the millions of tiny glass ampules meant one thing. To win the war, America had to cancel Christmas. The math was brutal. 22 million VT fuses. That is more than the entire population of Romania at the start of the conflict. This was not a side project. It was a national mobilization. The secret lived in the light bulbs. Before the war, factories across the Midwest churned out miles of colorful glass for holiday trees. Now, those assembly lines went dark, or rather, they went silent. Women in white aprons sat at long wooden benches. Their fingers moved with mechanical precision. They no longer handled festive decorations. They handled the hearts of a new weapon. A worker picks up a miniature radio tube. She solders a wire thinner than a human hair. She places the component into a reinforced casing. No one asks what the device does. The foreman watches the clock. The quota is tens of thousands per shift. Christmas lights vanished from store shelves. You could not buy a replacement bulb from Maine to California. The festive glow of American suburbs was traded for the cold, calculated efficiency of the proximity fuse. Was the sacrifice worth it? One shell costs more than 1,000 standard rounds. But one shell does the work of an entire battery. Axis intelligence felt the pressure. In Berlin and Tokyo, scientists scrambled to solve the puzzle of the smart shells. They knew the Americans had something impossible. They experimented with their own versions. They failed. The Allies were obsessed with secrecy. They built a failsafe into every fuse. If the shell missed its target, it did not fall to the ground to be found by a German patrol. It detonated in mid-air. The mechanism tore itself to pieces before the enemy could touch it. Every miss was a self-destruct. Every secret stayed buried in the clouds. Germany never managed to produce a single working unit. But 22 million devices meant 22 million chances for the enemy to steal the secret. The technology was a masterpiece of miniature violence. Inside the shell, a glass ampule shattered upon firing. Liquid spilled. A battery came to life. For a few seconds of flight, the projectile became a sentient hunter. It emitted a constant stream of radio energy, a miniature radar in a steel skin. When the signal bounced back from an enemy wing, the frequency shifted. At a precise distance, the circuit closed. The detonator triggered. What did the Allies fear more than missing a German plane? A dud. One unexploded shell landing in a Nazi-occupied field could end the war's greatest advantage. To prevent this, engineers installed a mechanical failsafe. It armed the fuse only after the shell cleared the barrel and traveled a safe distance. If the radar found no target, a self-destruction timer kicked in. The projectile killed itself in mid-air. It was the first time a weapon carried the same protocol as a high-ranking spy. Because of this paranoia, the High Command issued a total ban on using the fuses over enemy-held land. High Command chose the open ocean as their first testing ground. They feared a single dud. One unexploded shell on land meant the enemy could reverse engineer the radar. In the deep water, secrets stayed buried forever. On January 5, 1943, the cruiser USS Helena made history. It fired the first proximity fuses in combat. A Japanese bomber fell from the sky. One shot, one kill. The era of guessing the fuse timing was over. How many shells does it take to kill a plane? Before the VT fuse, gunners fired thousands of rounds for a single hit. Now, that number dropped to 150. Effectiveness skyrocketed 50-fold. This leap in efficiency saved enough steel and brass to build an entire secondary flotilla. The British deployed the technology to guard the coast. German V-1 flying bombs were the target. The results were clinical. Hit rates jumped by 80% overnight. The English Channel became a graveyard for German pulse jets. The ban on using these fuses over solid ground remained absolute for 21 months. Only in the face of a collapsing front did the risk of capture outweigh the cost of defeat. The restriction lasted until late 1944. The restriction on ground use finally broke in late 1944. When the Western Front began to crumble, Eisenhower demanded the ultimate edge. The secret technology moved from the hulls of warships to the frozen forests of the Ardennes. A German grenadier moves through the thick white fog. He feels safe. The mist hides him from American spotters. He stands tall, walking toward the Allied lines. Then, a sharp, metallic crack echoes in the air above his head. Not the thud of a shell hitting the dirt, a splintering explosion in the sky. How did the Americans find him in the fog? They didn't have to. 200,000 shells arrived at the front under a total security blackout. Artillery crews whispered the code name. Then they opened fire. The radio waves reached out from the nose of every projectile. They measured the distance to the frozen ground with perfect precision. The results were a massacre. Shrapnel rained down vertically at terminal velocity. It ignored the mud. It ignored the snow. A trench offered no sanctuary without a roof of solid timber. Even at the bottom of a foxhole, the steel rain found its mark. General Patton later wrote that the Battle of the Bulge would have cost double the American lives without this single invention. The German High Command received reports they could not explain. Their infantry was being erased by an invisible observer who never missed. By the end of the operation, the Wehrmacht's last great gamble had collapsed under the weight of 200,000 airbursts.